Since humanity first looked up, we've asked the ultimate question: what lies beyond the stars? Is there an end to it all, an edge to reality? We often talk about the edge of the universe, maybe picturing a cosmic wall or a final frontier. But is it really an edge, or just the limit of what we can see? In this journey together, we'll explore what modern cosmology tells us about this boundary. Forget simple walls. The reality science unveils is far more fascinating and, honestly, mind-bending. Our cosmic horizons have expanded dramatically over centuries, revealing a universe far vaster than ever imagined. Yet that fundamental question remains: what lies beyond the furthest thing our telescopes can detect? Today we dive into the science. We'll define the observable universe's edge, a limit set by light and time. We'll explore cosmic inflation, the theory explaining the universe's incredible scale. And we'll dare to ponder the possibilities: infinite space, complex cosmic shapes that might exist beyond our sight. So prepare for a voyage to the edge of knowledge itself. To venture beyond the edge, we first need to understand precisely what that edge is in scientific terms. As we touched upon, it's not a physical wall or a sudden drop-off into nothingness. Instead, the boundary we encounter is the edge of the observable universe, and this boundary is fundamentally defined by light and the finite time light has had to reach us since the universe began. Think about the ultimate speed limit in the cosmos, the speed of light in a vacuum, denoted by the letter CE. It's an almost incomprehensibly fast speed, about 300,000 kilometers or 186,000 miles every single second. Fast enough to circle the Earth more than 7 times in the blink of an eye. Yet, even at this incredible velocity, traversing the vast distances of the universe takes time, a lot of time. Light from our own sun takes about 8 minutes to reach Earth. Light from the nearest star system, Alpha Centauri, takes over 4 years. And light from the nearest major galaxy, Andromeda, has been traveling through space for 2.5 million years before reaching our telescopes. Now, combine this finite speed of light with another crucial fact. The universe itself has a finite age. Our best measurements tell us the universe burst into existence in the Big Bang approximately 13.8 billion years ago. So, if the universe is 13.8 billion years old, the absolute maximum distance light could have traveled to reach us since the very beginning is, well, 13.8 billion light years. This creates a conceptual sphere around us, centered on Earth, or more accurately, centered on any observer anywhere in the cosmos. Anything beyond this sphere is, in principle, unobservable today, simply because its light hasn't had enough time to complete the journey to us since the universe began. This sphere defines our observable universe. But there's a fascinating consequence of this light travel time. When we look out into space, we are also looking back in time. The further away we look, the further back in time we see. That galaxy whose light took 1 billion years to reach us, we see it not as it is today, but as it was 1 billion years ago. The galaxy whose light traveled for 10 billion years, we see it as a much younger version of itself, existing when the universe was only 3.8 billion years old. It's like having a cosmic time machine. The deeper we peer into space, the earlier the epoch of the universe we witness. So how far back can we look? What is the absolute earliest light we can detect? For about the first 380,000 years after the Big Bang, the universe was an incredibly hot, dense soup of charged particles and radiation. It was opaque. Light couldn't travel freely. Photons were constantly scattering off electrons like balls in a cosmic pinball machine. But as the universe expanded and cooled, protons and electrons finally combined to form neutral hydrogen atoms. Suddenly, the universe became transparent. The light that existed at that exact moment was set free, and it has been traveling across the cosmos ever since. Today, stretched by the expansion of space into microwave wavelengths, we detect this ancient light as the cosmic microwave background, the CMB. It's the oldest light in the universe, a faint afterglow of creation itself, bathing all of space. This CMB forms the ultimate boundary of our visible universe. the surface of last scattering. Now, here's where it gets even more mind-bending. You might think, okay, 13.8 billion years old, so the edge is 13.8 billion light years away. But that doesn't account for a crucial factor, the expansion of space itself. While that ancient light from the edge of the observable universe has been traveling towards us for 13.8 billion years, the space it has been traveling through has been stretching the entire time. Imagine 2 points marked on the surface of a balloon. As you inflate the balloon, the points move further apart, not because they are crawling across the surface, but because the surface itself is stretching. Similarly, the fabric of space-time has been expanding since the Big Bang. That region of space that emitted the CMB light 13.8 billion years ago has been carried much, much further away from us by this expansion. Taking this cosmic stretch into account, astronomers calculate that the current distance to the edge of our observable universe is actually about 46.5 billion light years. That makes the full diameter of the sphere we can theoretically see a staggering 93 billion light years across. 93 billion light years, that's an almost unimaginable expanse. Yet, and this is perhaps the most profound realization, there is absolutely no scientific reason to believe that this observable bubble is all there is. Our horizon is just that. Our horizon, limited by light and time, the whole universe, the entirety of reality, could be vastly larger. We might be living inside just one tiny patch of a potentially infinite cosmic ocean. What we can see is not necessarily the boundary of existence itself. So, what shaped this incredible scale? And what clues does the early universe give us about the true extent of reality? That leads us to the explosive idea of cosmic inflation. We've established the observable universe, a vast sphere 93 billion light years across, defined by the light that's had time to reach us. But we also noted that this immense region is likely just a small fraction of the total reality. How could the universe have become so incredibly large, far bigger than our observable patch? And how did it achieve such remarkable uniformity on large scales, with the cosmic microwave background looking almost identical in temperature in all directions? The answers may lie in a truly extraordinary event thought to have occurred in the very first moments of time: cosmic inflation. Imagine winding the clock back to the universe's infancy, to a mere fraction of a second after the Big Bang, something like 10 to the minus 36 seconds. According to the theory of inflation proposed by physicists like Alan Guth and Andre Linde in the early 1980s, the universe underwent an astonishing, almost unimaginable burst of hyper-expansion during this epoch. Driven by the energy locked within a hypothetical quantum field, the inflaton field permeating space, the universe didn't just expand, it inflated exponentially. Space itself stretched at a rate far exceeding the speed of light. In an infinitesimal sliver of time, a region far smaller than a single proton could have ballooned to macroscopic, even astronomical scales, perhaps the size of a grapefruit or, vastly larger. It's crucial to note that this superluminal expansion doesn't violate Einstein's theory of relativity. Relativity states that nothing can travel through space faster than light. Inflation, however, was an expansion of space itself. Think of points on the expanding balloon surface. The points aren't moving across the rubber faster than allowed, but the rubber between them is stretching, increasing their separation rapidly. This seemingly wild idea of inflation isn't just a theoretical fancy. It elegantly solves some of the biggest puzzles that plagued the standard Big Bang model. First, the horizon problem. As we saw, the cosmic microwave background radiation is remarkably uniform in temperature across the entire sky, varying by only tiny fractions of a degree. In the standard Big Bang model, without inflation, regions on opposite sides of the sky today were too far apart in the early universe to have ever exchanged heat or information traveling at the speed of light. So, how did they know to end up at the same temperature? Inflation solves this beautifully. Before the inflationary burst, The region destined to become our entire observable universe was incredibly tiny, small enough for everything within it to be causally connected and reach a uniform temperature. Inflation then stretched this tiny uniform patch to enormous cosmic scales, preserving that initial uniformity across vast distances we observe today. Second, the flatness problem. Observations strongly indicate that the geometry of our universe on large scales is very close to being perfectly flat, meaning it follows the rules of Euclidean geometry we learn in school, where parallel lines stay parallel and the angles in a triangle add up to 180 degrees. According to general relativity, the universe's geometry is determined by its total density of matter and energy. For the universe to be so incredibly close to flat today, after 13.8 billion years of expansion, its initial density in the very early universe must have been fine-tuned to the critical density value with almost unbelievable precision. Like balancing a pencil on its sharpest point for billions of years. Why this extraordinary fine-tuning? Inflation provides a natural explanation. Just as inflating a balloon stretches its surface, making it appear flatter locally, the immense stretching during inflation would have driven any initial curvature of space, whether positive like a sphere or negative like a saddle, towards near-perfect flatness. Inflation makes a flat universe the natural outcome, not a bizarre coincidence. Inflation also potentially solves other issues, like the predicted abundance of exotic particles called magnetic monopoles, which, should have been created in the early universe according to some theories, but have never been observed. Inflation would dilute their density so drastically that honestly finding one in our observable patch would be virtually impossible. But perhaps the most crucial implication of inflation for our question, what lies beyond the edge, is its impact on the sheer scale of reality. If inflation happened, it strongly suggests that the total universe, the entirety of space-time generated, is vastly, unimaginably larger than the 93 billion light-year sphere we can observe. Our observable universe is just one patch, one inflated region within this potentially colossal metastructure. What lies beyond our horizon, according to inflation, is likely just more universe born from the same inflationary process, looking statistically similar to our own region, stretching far beyond our view. And there's one more incredible piece to the puzzle. Inflation doesn't just explain the universe's size and flatness, it also provides the seeds for all the structure we see today. According to quantum mechanics, even empty space isn't truly empty. It's a sea of fleeting quantum fluctuations, tiny, unpredictable variations in energy. During the inflationary epoch, these microscopic quantum jitters were stretched to enormous astrophysical scales. Tiny variations in density and energy from point to point became vast ripples across the cosmos. These slight overdensities, amplified by gravity over billions of years, acted as the gravitational wells that pulled matter together, eventually forming the first stars, galaxies, and the intricate, web-like structure of the universe we observe today. The largest structures in the cosmos have their origins in the quantum weirdness of the universe's first moments, magnified by inflation. The predictions made by inflationary models, a flat universe, the specific pattern and scale of those initial density fluctuations match our observations of the cosmic microwave background and the large-scale distribution of galaxies with stunning accuracy. While the exact physics driving inflation, the precise nature of the inflaton field, remains a mystery and an active area of research, the inflationary paradigm has become a cornerstone of modern cosmology, providing a compelling narrative for the universe's earliest moments and its subsequent evolution into the vast, structured cosmos we inhabit. So, inflation paints a picture of a universe far grander than we can see. But what does that mean for what lies beyond our horizon? Could it truly go on forever? Or could space have a more complex shape? Let's explore the possibilities. Cosmic inflation paints a picture of a universe vastly larger than our observable bubble, born from an infinitesimal speck that ballooned outwards. It suggests that beyond the edge of what we can see, there isn't a sudden stop, but simply more universe. But what form does this more universe take? Does it stretch on endlessly, or could reality have a more intricate structure? Let's delve into the scientifically plausible yet profoundly mind-bending possibilities. One compelling possibility, strongly supported by our current best measurements, is that the universe is spatially infinite. Observations, particularly from the Planck satellite mapping the cosmic microwave background, indicate that the geometry of space-time on the largest scales is remarkably flat. If the universe is perfectly flat, and assuming the simplest topology, then it likely extends infinitely in all directions. Imagine setting off in a spaceship in a perfectly straight line. In a truly infinite and flat universe, you would simply travel forever, passing endless galaxies, clusters and voids, never returning, never reaching any kind of boundary. Beyond our observable horizon would just be more space, more matter, more energy, governed by the same physical laws we see operating within our cosmic neighborhood. It's a staggering thought, an unending ocean of existence. Why does flatness suggest infinity? Think about geometry. On a positively curved surface, like a sphere, parallel lines eventually meet. On a negatively curved surface, like a saddle, they diverge. Only in a flat Euclidean geometry do parallel lines remain forever parallel. While our measurements show the universe is very close to flat, we can't measure it with perfect, infinite precision. It could have a very slight curvature, meaning it might be finite, but just incredibly vast. However, the simplest interpretation of the data, and the one often favored by Occam's razor, is true flatness, implying true infinity. Now, if the universe truly is infinite and contains a roughly uniform distribution of matter and energy, as large-scale observations suggest, the implications become utterly astonishing, bordering on the philosophical. In an infinite space with a finite number of ways particles can be arranged within any given volume. Due to quantum states, simple statistics dictates that any possible arrangement must occur, not just once, but infinitely many times over. Think about that. Somewhere out there in that infinite expanse far beyond our horizon, there would be other regions of space identical to our observable universe. There would be regions where everything is almost identical, but perhaps you chose differently this morning. There would be regions differing more significantly and regions utterly alien. According to this logic, there would be infinitely many copies of you living out identical lives, and infinitely many living out every possible variation. This isn't science fiction, but a potential, albeit debated, consequence of combining infinite flat space with the principles of quantum mechanics and thermodynamics. It's sometimes called the Boltzmann brain problem's cousin, the statistical inevitability of repetition in an infinite system. However, it's crucial to stress that these hypothetical identical regions would be separated by distances so immense, likely vastly larger than our entire observable universe, that they would almost certainly remain forever causally disconnected from us. We could never reach them, nor they us. They exist as a statistical possibility in an infinite framework, not necessarily as parallel worlds in the science fiction sense. But what if the universe isn't infinite? Is the only alternative a universe with a hard edge? Not necessarily. Geometry and topology offer another fascinating possibility, a universe that is finite in volume but has no boundary, no edge to run into. How can that be? Consider again the surface of a sphere. It has a finite surface area, but you can travel across it indefinitely without ever falling off an edge. It's finite, yet unbounded. Our three-dimensional space, could in principle possess a similar, albeit harder to visualize, property. It could have a non-trivial topology, meaning it connects back to itself in some way. Imagine living inside a colossal three-dimensional donut, a 3 torus. If you traveled far enough in one direction, you might eventually find yourself right back where you started, having circumnavigated the universe. Other more complex topologies are also possible, like the intriguing Poincaré dodecahedral space, where the universe would be finite and shaped like a slightly curved 12-sided die with opposite faces identified. If our universe had such a finite wrap structure, how could we possibly detect it? If the universe was smaller than our observable horizon, or not much larger, we might be able to see evidence of this cosmic wraparound. Light from very distant objects could reach us from multiple directions, creating duplicate images of the same galaxies or quasars in different parts of the sky. It would be like living inside a giant hall of mirrors. A particularly powerful test involves searching for specific patterns in the cosmic microwave background. If the universe is finite and wrapped, the largest fluctuations in the CMB might be limited by the universe's overall size. Furthermore, we might expect to see pairs of matching circles in the CMB map representing where the surface of last scattering, where the CMB originated, intersects itself from our perspective due to the wraparound topology. Scientists have, meticulously searched the data from the WMAP and Planck satellites for these circles in the sky and other topological signatures. So far, these searches have come up empty-handed. There has been no statistically significant unambiguous detection of cosmic topology. The observations are consistent with a universe that is either truly infinite and flat, or finite but so immensely large, far bigger than our observable horizon, that any wraparound effects are just too subtle for us to detect with current instruments. While the possibility of a finite, unbounded universe remains open and, intriguing, the evidence currently leans towards vastness, potentially infinite vastness. This leads us to a deeper, perhaps more philosophical question, whether the universe is infinite or just incredibly vast and finite but unbounded. Does it make sense to ask what lies beyond its physical extent? If there is a limit to space-time itself, what is that limit bordering? Is it just nothing? But what is nothing in this context? Is it simply empty space, devoid of matter and energy, but still governed by physical laws? Or is it something far more profound, the absolute absence of space, time, matter, energy, and even the laws themselves? Can we even conceive of such a state? Some physicists speculate about concepts like a larger bulk space-time in higher dimensions, within which our universe might be embedded like a membrane or brain. Others argue that asking what is outside the universe might be a meaningless question, a bit like asking what is north of the North Pole. If the universe encompasses all of space-time, then, there is no outside in a spatial sense. The concept simply might not apply. These questions, really push the boundaries of physics and philosophy. While we can speculate about infinite repetitions or cosmic wraparounds based on mathematical models and observations within our horizon, the nature of reality beyond that horizon remains shrouded in mystery, and perhaps our ability to ever know is itself limited. We've journeyed through concepts of infinity and cosmic topology, speculating on the grand structure of reality far beyond our direct view. But it's essential as scientists to circle back to what we can actually know, and importantly, the inherent limits of our knowledge. It's crucial to constantly distinguish between the edge of the observable universe and any hypothetical physical edge to reality itself. The boundary we've discussed extensively, that sphere, roughly 93 billion light-years across, is fundamentally an observational horizon. It's defined by the finite speed of light and the finite age of the universe. It represents the maximum distance from which light traveling since the Big Bang has had time to reach us today. It is our limit, a consequence of our place in space-time, not necessarily a boundary inherent to the cosmos itself. And there's another profound, perhaps slightly melancholic aspect to our cosmic horizon, driven by a mysterious force shaping the universe's ultimate fate, dark energy. Since the late 1990s, observations of distant supernovae have revealed that the expansion of the universe isn't slowing down due to gravity, as was long expected. It's accelerating. Space itself is stretching apart at an ever-increasing rate, pushed outwards by this enigmatic dark energy, which seems to make up nearly 70% of the universe's total energy density. This accelerating expansion has a startling consequence for our ability to observe the distant cosmos. Galaxies beyond a certain distance, known as the cosmic event horizon, are receding from us faster than the speed of light. And just to be clear, this is space expanding, not the galaxies moving through space. As time goes on, the light emitted by increasingly distant galaxies will be stretched so much, and their recession velocity will become so great that it will never be able to reach us, no matter how long we wait. Effectively, these galaxies will disappear beyond our future horizon, forever lost to view. Over unimaginable timescales, if this acceleration continues, our observable universe will become an increasingly lonely place. Distant galaxies will redshift out of sight, leaving only our local group of gravitationally bound galaxies visible against an otherwise empty void. Our window onto the vast cosmos will, in a sense, shrink in terms of the new information we can gather from the farthest reaches. So given these fundamental limits, the finite speed of light, the finite age of the universe, and the accelerating expansion driven by dark energy, can we ever truly, definitively know what lies beyond our observable horizon? Can we ever confirm if the universe is infinite, or if it has a complex topology, or what might constitute the nothingness outside of space-time, if such a concept even applies? Perhaps not directly. We may always be confined, in a sense, to observing the consequences of the universe's structure and history from within our cosmic bubble. We might never receive a direct signal or image from beyond the edge of observability, but that doesn't mean the quest for knowledge stops. Science constantly pushes against these boundaries. We refine our models, develop new observational techniques, like using gravitational waves or neutrinos, which travel differently than light, and devise clever ways to test the implications of different cosmological scenarios using the data we can gather. Asking what lies beyond is not just an idle question. It is a fundamental driver of scientific progress. It fuels our innate human curiosity, the same curiosity that led our ancestors to map the stars and explore the Earth. It pushes us to build more powerful telescopes, design more sophisticated experiments, and develop deeper theoretical frameworks. The very act of grappling with these ultimate questions, about the origin, structure, and fate of the cosmos, about the nature of reality itself, deepens our understanding of the universe we do inhabit. It forces us to confront the limits of our intuition and develop new ways of thinking. The quest itself, the journey towards the edge of knowledge, holds immense value, even if the final destination, the ultimate answer, remains perpetually just beyond our grasp. It reminds us of our place in the vast cosmic tapestry, small perhaps, but capable of comprehending so much and driven by an insatiable desire to understand even more. The edge of the universe, then, is as much a boundary within ourselves, the limit of our current understanding, as it is a physical concept in space-time. As we conclude our journey, let's reflect on what we've explored and, embrace the profound mystery that still remains. Our cosmic journey has taken us from the familiar night sky to the very edge of observability and into the realm of profound cosmological questions. So what lies beyond the edge of the universe? We've learned it's not a simple wall, but a horizon defined by light and time. Beyond that horizon, the universe likely continues, perhaps stretching into infinity, mirroring the flatness we observe, or maybe it wraps back on itself in some complex finite topology, a cosmic labyrinth we are yet to map. We explored how the theory of cosmic inflation provides a compelling explanation for the universe's vast scale and structure, suggesting our observable patch is just a tiny fraction of the whole. We've confronted the limits of our knowledge, the accelerating expansion that may eventually hide distant galaxies from view, and the deep philosophical questions about the nature of existence itself. The ultimate truth about what lies beyond our cosmic horizon remains tantalizingly out of reach. We simply don't know for sure, and perhaps that is the most beautiful and exciting part. The universe retains its deepest mysteries, not as barriers, but as invitations to keep exploring, keep questioning, keep learning, and honestly keep wondering. The edge of the universe ultimately isn't just a physical location in space-time. It represents the ever-advancing frontier of human understanding. It's a testament to our relentless curiosity and our capacity to probe the grandest scales of reality. What do you think lies beyond? Does the idea of an infinite universe thrill you or daunt you? Do you suspect a hidden cosmic shape? Share your thoughts and speculations in the comments below. Let's continue the conversation. If you enjoyed this journey to the edge of knowledge and back, be sure to subscribe right here to Space Matters for more deep dives into the universe's biggest questions and most profound mysteries. Keep looking up.